Okay, we are now recording. Welcome to the electronics class for September the 24th. Holy cow, the 24th already. Time sure flies. Okay, so I was just looking through Canvas here, looking at what you guys turned in for the midterm exams. Uh, I went through earlier this morning and I graded all the midterm exams that were turned in as of this morning, which really had me frightened there because it was a tiny number. I see it looks a whole lot better now. There's still a couple of you who haven't turned them in. I'm not going to name any names, but shame on you if you're one of those that didn't turn them in. Where's your excuse? And the rest of you, it looks like we got a whole bunch of you that just did it in the last hour. Boy, you sure like leaving things for the last minute, don't you? Okay, so I haven't graded those, but of the ones that I graded this morning, it looks like you guys got it pretty well. So congratulations. I think I think that this is pretty straightforward. Now, I do not intend to go over the answers to the midterm right at this time. There are still a few of you who haven't done it. And so I don't want to go over the answers because that would give it away. I'll wait until next time and we'll talk about the answers to it next time. I will say that I was pleased to see the variety of the ways that you guys did it. And that's actually what I was really hoping for. Somebody else just came here. Let me just mark you real quick here. All right. Okay. All right. So I was very pleased with the variety of the solutions that I saw. Most of you did the job using 3 resistors per breadboard, which is the straightforward and easy way to do it. But some of you used only 1 resistor per breadboard. And I was very glad to see that. That showed creativity. And I was really, really pleased that some of you showed the initiative to go the extra mile and figure out a way that you could do the job using only 1 resistor per breadboard.
Let's
In
take a
fact,
minute.
Go ahead.
Let's take a minute to talk about how you took the easy way.
I did it both ways, actually, just for grins. The one that I
Yes,
showed you.
but in the example, you took the easy way.
Yeah, yeah. Now, those of you that did it where you turned on more than 1 resistor or more than 1 LED at the same time, some of you sent me an email saying, hey, wait a minute, Mr. Hendricks, this is weird because when I only turn on 1 LED at a time, then I get 20 milliamps just like you did in the class. But when I turn on 2 at a time or 3 at a time, the current that I get on mine is different than the current that you got on yours. What's the deal? Well, the difference is because when you hook things up using only 1 resistor, the electricity flows through a different path. And so as long as you only have one at a time, you don't notice any difference. But if you turn on 2 at a time, you will notice a difference because the path is different and it has very important consequences. And not coincidentally, that is exactly what we are going to talk about in today's class. Up until now, all of the circuits that we've dealt with have been what are called series circuits. So there's only 1 branch and all of the electricity has to flow through that 1 branch. So the current is the same everywhere in the branch. Well, that's not going to be the case starting today. We're going to talk about circuits that have more than 1 branch. So, you can have a place where the circuit is coming into a little junction here and some of it goes one way and some of it goes the other way. And that is exactly what you guys experienced when you were hooking up your LEDs. If you hooked it up using 1 resistor instead of 3 resistors, that's exactly what caused that strange performance. So I'm ready to jump into today's material, but I will pause for just a second to say, does anybody have any questions about anything? Now, I don't want to actually give the answer to the test right now. I'll do that next time we meet. Oh, I know. Those of you that didn't turn in your test, okay, you're probably wondering, what am I going to do to you? Okay, well, here's the deal. You cannot get an A on the test. or even a B, I think. I think even giving you a B on the test would be too generous. You should have got the test turned in on time. So what I'm going to tell you is the best you can hope for now is to get a C. In order to get that C, you're going to have to turn in a circuit that does everything that I wanted done. So if the reason you didn't turn one in was because you didn't know how to do it, that's okay. Send me an email and I will help you. So that we'll make sure that you get it. Now, unfortunately, I can't give you an A, but I could at least give you a C. So send me an email if you need. And then next time we meet, which by the way is going to be Tuesday of next week, next time we meet, I am going to go over the answers. And from that point on, I'm not going to allow you to turn them in. So if you haven't got it turned in by next time we meet, it's just going to be an F and it's going to stay an F. So make sure you get it turned in. Okay, questions? Going once, going twice, sold. Okay, well, let's go into the new material for today. Let me get my Canvas booted up here. Okay, and now I'll share my screen. All right, so you should now be seeing my Canvas page. So let's click on electronics. And come on, kind of slow. All right, there we are. So here's the electronics page. Let's go down to assignments, quizzes, and tests. All right, don't worry about that one. That one doesn't apply to you. Okay, so getting started, we did that. Basics, concepts, and definitions, we did that. So the module we just finished is this one. Good. I hate when Canvas jumps around like that. Okay, so basic concepts and definitions, we did that a while ago. Module 2, series circuits, we are now finished with that. And so we just took the test on that. So now we're going to start into module number 3, which is parallel circuits. And also we're going to include, so after we get good at parallel circuits, then we're going to mix the two together. We're going to have circuits that are a combination of series connections and parallel connections hooked up together. But we're going to start off with just basic, simple parallel circuits. All right, so this is up on Canvas. Note the deadline here. The deadline is September 29th, which is next time we meet. So if we click on simple parallel circuits, it takes us to here, which looks a little different from what you're going to see. So if I click on preview, then it'll make it look a little bit more like what you would actually see. Okay, so notice it is a quiz, like all of our previous assignments have been. So, oops, I don't want you to actually see the quiz question there. Let's move it down here. So, okay, so don't want you to see what the quiz question is yet. All right, so you'll notice that we're going to be reading a section out of the textbook, out of our online textbook. But notice that you don't need to read the whole thing. There's a place where they talk about this program they use called SPICE. I don't use that program. I don't see that it's particularly valuable. I mean, I can understand, yeah, in some ways it's kind of nice, but I'd say let's just not even worry about it. So whenever they talk about this special program they have called SPICE, ignore it, okay? But you do need to read the first part. So let's go ahead and let's click on the link here, and it'll take us into the online textbook eventually. All right, simple parallel circuits. And here's our little advertisement. You know, when you use a free textbook here, you got to put up with advertisements. By the way, this advertisement is from Texas Instruments, and they make really cool electronics equipment, testing equipment. This thing right there, that's an oscilloscope. Very cool. We are going to be learning how to use oscilloscopes going forward. Okay, so a series circuit, like I said before, is one where all of the current flows through the same branch. So if I were to draw a circuit on the screen down here, in the lower right of the screen here. So here's my battery. Okay, here's a resistor, and I might have another resistor. Okay, and who knows, I might even have a third resistor, and I might have a fourth resistor, but I only have one branch. So all of the current that flows through the, actually, let me make that a little bit fatter here. Okay. So all of the current that comes out of the battery has to go through that resistor. It comes out the other side. And again, all of the current goes through that one, and all of it goes through that one, all of it goes through that one. So every single resistor in the circuit has the full current going through it because there's only one branch. There's nowhere else that the current could go. Well, that's not going to be the case now. So what we're going to do today is we're going to do circuits like this. And let me make it just a little bit larger here. Okay, so if we track the path of the current here, okay, so the current comes out of the battery, goes here, and here is something called a junction. So get used to that word. We're going to be talking about junctions a lot in this class. So this is a junction, this is also a junction, and this is a junction down here, and this is a junction down here. All of these guys are all junctions. So a junction is where the path either splits or where we have multiple paths that come together. All right, so when the electricity comes to a junction, then it can split. So some of it can go this way and some of it can go that way. And so everything that we learned about series circuits, well, a lot of what we learned about series circuits is not going to apply anymore. All right, so we can see that, let me switch to different colors here. It might help make things a little clearer to understand. Okay, so some of the current is going to flow down here and then back to the battery. Okay, and other parts of the current are going to come over here, and oh my goodness, look, we got yet another junction. Okay, so that means that some of that current is going to go down here, and then here it's going to combine with the red current and go in there. But others of the current is going to come over here, and then here it's going to combine with the yellow, and then here it's going to combine with the red. And so once we get back to this point again here, we now have the full current again. So if we're going to stick with our color codes here, maybe I could call that blue, because that's what we started off. So, oops. Okay, so here, oh, come on, that's not what I wanted. Hang on. Okay, so in this branch of the circuit here, all of the current is the same. And so how about let's give that a name. Let's call this I total. Okay, so that where you see in the kind of bluish color there, that is the total current. When we come to junction number 2, some of the current goes down this way. So let's call, now since this is labeled R1, let me suggest that we call this current, let's call this I1. All right, and then some of the current comes down this way. And so this current is going to be whatever I total minus I1 is. Okay, now we come to a junction. So again, some of the current is going to go down this way. So since this is called resistor 2, how about let's call this I2. And then some of it's going to go over here, and notice this is R3. So I would recommend we call this current I3. Okay, so hopefully you guys recognize that the total current, so I total, is going to equal I1 plus I2 plus I3. Okay, I hope that makes sense, because at junction number 2 here, I1 goes down that way, and then what's left is I total minus I1. And then we get to here, I2 goes down that way. And then what's left is I total minus Y1 minus I2. And so that means I3 must be I1, I total minus I1 minus I2. Okay, this guy right here is very important relationship. I trust that it makes sense to you guys that that would be the case. Let me check the chat box here. I'm not seeing any questions in the chat box. Okay, not hearing anything. All right. So now, back when we were learning about series connections, we used the rule, and let me turn on annotation again. Okay. So when we were hooked up in series, you may remember that we said that the total resistance was equal to R1 plus R2 plus R3. So if we only had one resistor, so let me get rid of this. Let's say we've only got one resistor, okay? So when we added the second resistor on there, R2, the total resistance went up, which makes sense because if you're in series, okay, so there's the resistor, there's the other resistor. So this battery, it has to push the current through that resistor, and it also has to push the current through that one. So if you connect two of them together, the battery clearly is going to have to push harder in order to get the electricity to flow through it. So you might think that something similar would be the case with parallel circuits, but it's not. Actually, it works the other way around. If you have a parallel circuit, so let me get this out of the way here. Okay, if you have a parallel circuit like this, and so you've got R total, and you start off with only one resistor, okay? When you add on that second resistor, R total does not go up. It goes down. And a lot of students have trouble with this. So let me stop for a second here so I can look you in the eye here. A lot of students get really perplexed. They say, wait a minute. If we're adding resistance, shouldn't the total resistance go up? And they say, that doesn't make any sense. Well, here's the way to think about it so it will make sense. When we add a resistor, we are not only adding a resistor, but we are also adding a new path that wasn't there before. And it's the new path that makes the difference. Okay, so here's our battery, here's our resistor. Okay, so this is R1. Okay, so when we add that second resistor in there, we're also adding in a path that wasn't there before. So if this battery is trying to push the current, so let me just do something here. Okay, so this battery is trying to push the current through that resistor. As soon as we added this extra guy here, we now added an extra path so that it makes it easier, not harder, for the battery to push electricity through the combined circuit. Because even though this resistor here may be a really high value resistor with lots and lots and lots of ohms, doesn't matter. It's a path that wasn't there before, and that path is now there. And so that battery is going to say, oh, the resistance went down, not up. Okay, so with that, the rule before for a series circuit was that R total equals R1 plus R2 plus R3 plus dot, 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 as many resistors as we have. So for a parallel circuit, we know that this up here does not work. We're going to have to come up with an equation that does work, because in your homework tonight and for the rest of the year, you're going to have times where you're going to have to calculate what is the resistance when they're hooked up in parallel. Does anybody know what is the formula that we can use to find the total resistance when they're hooked up in parallel rather than in series? Nobody wants to admit it? Okay, well, let's figure it out. Let's see if we can figure out what that equation must look like. Oops. Oh, okay. Well, I might as well just, okay. All right. So here we go. So here is a nice simple circuit, one resistor. So that's R1. Okay, so we're going to add on another resistor, but this time we're going to add it in parallel. So we got R2 now. Okay, so the way to figure this out is instead of looking at the resistance, let's look at the current. Ah, yes, Jasper, you're kind of sort of on it, but not quite. But you're going in the right direction there, Jasper. Okay, so let's look at the current. And so let's see. So if we've got, let me do it in a different color here. So here's the current coming out of the battery. So I'm going to call that I total. Okay, and the current is going to split, and some of it's going to go this way. So let's call that I1. And the rest of the current is going to come and go that way. So let's call that I2. So do you guys agree that I don't want it that fat. Let me switch to a thinner pen here. So do you guys agree that I total equals I1 plus I2? That's supposed to be a 2. You guys agree that makes sense? Because of this junction right here. We know that the current coming in has to equal the current going out. The current coming in is I total. The current going out is I1 and I1 plus I2. Okay? All right. So now I total, okay, what I'm going to do for a second here is I'm going to take our real circuit that has 2 resistors in it, and I'm going to replace that with an imaginary circuit that has only 1 resistor in it. And this resistor is what I'm going to call R total. So this 1 resistor is really the equivalent of these 2 guys hooked up in parallel like that. So if I wanted to know what R total is, so the battery is V, or your book likes to call it E, but I prefer to call it V because most of the books that I've worked with call it V, but recognize that it's either way. Okay, so if you've only got 1 resistor and 1 battery, then you know that I total must be equal to V divided by R total. Okay, and now let's look at I1. In fact, my picture is getting a little cluttered here. Let me see if I can clean it up a bit. Okay, so let's look at I1. Well, if I've got a battery, let's say this is a 12-volt battery. It doesn't have to be 12, could be anything. Anywhere on this wire, the voltage there is going to be the same. If it's 12 volts here, it's going to be 12 volts here. It's going to be 12 volts here, 12 volts here. Anywhere we go on this wire, it's going to be 12 volts until we come to a resistor. When we cross over a resistor, that's when the pressure changes. That's when the voltage changes. But as long as we haven't hit any resistors, anywhere on this wire, the volts are going to be 12. And now on the other side of the battery, that side is always by definition 0. So the same thing applies. Anywhere on the wires down here, the voltage is always 0. Okay. So if I look just at I1, the voltage, the drop that I have across I1, well, I got 12 on this side, I got 0 on that side. So the voltage across I1 is the same as the voltage of the battery. And by the way, the same thing is true for I2. Voltage across that's the same. So if I want to calculate what I1 is, it's going to equal whatever the voltage is across I1, which in this case is the same as the voltage on the battery, divided by whatever R1 value is. Okay, because we know Ohm's law tells us whatever is the voltage drop across this resistor, well, okay, that can be used together with Ohm's law to figure out what is the current through that resistor. So same thing applies for I2. I2 is going to be just whatever is the voltage across R2, which is V, divided by R2. So if we take this equation, what would happen if I were to multiply the left side by 1 over V Or in other words, what if I divide by V? And I do the same thing on the right side, because whatever I do the left side, I have to do the same on the right side. That's the rules of math. So that V cancels that. This V cancels both of those. And so what am I left with? I'm left with 1 over R total equals 1 over R1 plus 1 over R2. And if I had a third resistor, it'd be plus 1 over R3. Oops, I kind of ran out of space there. Wonder if I can make that bigger. So let me do that. Okay, plus 1 over R3 plus dot, dot, dot. So this right here, this is the magic equation that we're going to use to calculate what is our total. Does that make sense where that comes from? Okay, I'm not hearing any complaints, right? So here's the rule. If you've got resistors that are connected in series, then R total equals R1 plus R2 plus R3 plus dot, 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 dot. If, however, they're connected in parallel, then the rule is 1 divided by R total equals 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. That's supposed to be an R plus dot, 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 dot. Okay. If you know that, then you will be in good shape for doing tonight's homework. Okay. All right. So now let me go back here and share this again. All right. So let's figure out what is the total resistance of this circuit that you see right here. So if I were to take my real circuit, which has 3 resistors hooked up in series, and if I were to replace that with an imaginary circuit where I've got my battery, which is a 9-volt battery, but instead of having 3 resistors there, I only have 1 resistor, and I'm going to call that R total. So I want to know what is the value that this 1 resistor would have to have so that my battery right here and my battery right here feel the same resistance. So think of it this way. Imagine the batteries don't have eyes, which is pretty easy to imagine because batteries don't have eyes. And so if there's like a curtain right here, this battery cannot see with its eyes what's on the other side of the curtain. It can only feel it. Okay, so it is trying to push electricity through this circuit, coming out this way, and it can't see what's on the other side of the curtain. It can only feel it. So if we do our job right, the battery on the right here will feel the exact same resistance that the battery on the left would feel. But we have to do our job right. Okay, so we need to calculate using the formula that we just derived. We need to calculate what the resistance would be. So I'm hoping that some of you guys are way ahead of me. Has anybody got a number yet for what our total would have to be? I'm going to give you a minute or maybe 2. I want you guys to see if you can come up with a number for what would our total have to be in order for the battery on the right to feel the same resistance that the battery on the left feels. Okay, so I'm seeing one answer. Okay. Now, Jasper, did you recognize that the resistances on our drawing here are not in ohms? Those are in kilo ohms. Did you notice that? So this is not a 10 ohm resistor, it's a 10 kilo ohm. This is not a 2 ohm resistor, it's a 2 kilo ohm resistor. So Jasper, I recommend you go back and do it again. How about somebody else? Okay, Eric, I like what you've done. I'm not saying it's right or not, but I see that you've got something there. But I also noticed that you wrote it as a fraction. In this class, I want answers that are in decimal form. So please do it again, but give it to me in decimal form, not fraction form. And the rest of you guys keep going. I want everybody to answer this question. Not just Jasper and Eric. I want other people to answer it too. I'll give you one more minute here. I'm a little bit concerned. Okay, now I'm seeing a number. Okay, but he's got a question mark by it. So that tells me he's probably not very confident in it. And Eric, I wonder if maybe you also forgot that these resistance values you see on the screen right now, those are kilo ohms, not regular ohms. So I think that's going to make a big difference. Okay, now Presley has an answer. Okay, and the answer actually sounds to me like it's in the right ballpark. Presley, would you be willing to walk us through how you got that answer? Unmute yourself here.
I mean, I mostly did a random calculation until it came close to what the other people got. I'm completely guessing here.
Okay, a random calculation until you came close. Okay, well that worries me. I would prefer that we didn't do random calculations until we came close. All right, so how about if I walk us through this? Okay, so I am going to start with the equation that we just derived so we recognize these guys are hooked up in parallel. So the equation says that 1 over R total equals 1 over the first resistor, which I'm going to write as 1 over, so 10K is 10,000. Okay, plus 1 divided by the second one. So remember, 2K is really 2,000. Plus 1 divided by the third one. And remember, 1K is really 1,000. Okay, so now when I get out my calculator here, I type in 1 divided by 10,000 plus 1 divided by 2,000, okay, plus 1 divided by 1,000, okay? And when I hit enter, the number on my calculator is 0.0016. And some of you might be tempted to say, well, that's the answer. But is that our total, or is that 1 over our total? Well, hopefully you realize that number that I have on my calculator right now is actually 1 over our total, which is not what I wanted. Okay, so I trust you guys are good enough at math to recognize that 0.0016 is the same thing as 0.0016 divided by 1. So if I've got two fractions here, what I can do is I can flip them. So if I just flip the R total, so it goes from bottom to top, well, I can do that as long as I flip what's over on the other side too. So what that tells me then is that R total is equal to 1 divided by 0.0016, okay? And so if I put that into my calculator, so 1 divided by whatever my last answer was, so I get 625, okay? All right, so Brian and Isaiah and Tristan, good for you. Presley, now Presley wrote his answer as 630, which I think is a better answer. Do you guys know why that's the case? It all has to do with what we call sig figs. Yes, Tristan, you got it exactly right. Sig figs. Okay, so if we write the answer as 625, that means that we think that the answer is accurate to 3 significant figures. We are fooling ourselves if we think that's the case, okay? Look at this number right here. How many sig figs do you see in that? Hopefully you say 1. Look at this number right here. Some of you might think that that number has two significant figures. It doesn't. It has two digits, but that 0 there is really just a placeholder. So this number only has one sig fig. This number only has one sig fig, this one. So our input numbers to our calculations here, they only have one significant figure. So if we put our answer with 3 sig figs, we are smoking something. And in fact, even if we put it with 2 sig figs, even that is not really accurate. The best way to answer this would be to say with 1 sig fig, because you can never have more significant figures in your answer than you do in the input numbers. So even though 625 is the number that appears on our calculator, we really should report it as 600. Okay. Now, if we wanted more accuracy, what we could have done is we could have said, now let me just give me a sec to erase all these guys here. Okay. So if the person who wrote the problem said that the voltage here is 9.00, then it has 3 sig figs in it. Those zeros that you see over there, those are not placeholders. Those are significant. And so this one right here, if we wrote that as 10.0 kilo ohms, okay, then it would have 3 sig figs. If we wrote this one as 2.00 kilo ohms, then it would have 3 sig figs. This one is 1.00 kilo ohms. Okay, so if our input numbers had 3 sig figs, then I would report my answer as 625. Okay, but since it wasn't, it was 600. Now, I realize that a lot of you guys are new to this whole sig fig thing. Any of you who have had chemistry or physics, you guys should know about sig figs. So for you guys, I'm going to insist that you follow the sig fig rules. But if you are brand new to this, we have several 9th graders in here, and if you're a 9th grader, you're in a biology class right now, this whole thing about sig figs is probably brand new to you. So if you were to report the answer as 625, I wouldn't mark it wrong for you. But those of you that have had chemistry and physics, okay, I want you guys to use the right rules for sig figs. Okay. All right, so let's go back to our textbook here. All right, so in the textbook here, they talk about how to calculate what we just did. And you'll notice the important thing that they mention in the textbook here is that whenever you have parallel circuits, the voltage is equal across all components in the circuits, okay? That is going to be the case. So if we come back here, okay, you'll see that all 3 of these resistors, okay, give me just a sec. All 3 of these resistors are connected to this wire right here. And this wire right here goes directly to the plus side of the battery with no resistors in between. Now, if there was a resistor right here, okay, then that would make things more complicated. Or if there was a resistor right here, okay, that would make things more complicated. And by the way, next week we will start learning how to deal with those, because those are real world situations that you do need to know how to deal with. But for right now, we're going to keep everything really simple. So we're going to say this wire right here is connected directly to the plus side of the battery. And so if we were wiring this up on a breadboard, I would insist that you make that wire be red, because that is a rule for electronics. And in fact, it's actually a legally enforceable rule. If you were to enter, if you were to join up with our robotics team, where we build a robot that we enter in this international competition, before we're allowed to put our robot onto the field and turn the robot on and let it run around, we have to pass an inspection. And one of the rules that we have to pass is that any wire that is connected directly to the plus side of the battery, so that the voltage on that wire is always equal to whatever the voltage on the battery is, that wire must be red. If that wire is not red, they will fail the inspection and they won't let us onto the field. And then the same thing with any wire that's connected to the negative side of the battery. That wire must be black. If it's not, we will fail the inspection and they won't let us onto the field. So I'm going to start doing those same rules with you guys. When you connect up circuits using Tinkercad, okay, any wire that is connected directly to the plus side of the battery must be a red colored wire. And any wire that is connected directly to the minus side of the battery must be a black colored wire. So anybody who looks at your circuit, they know that any wire that's red, so if you got a 9-volt battery, okay, anybody looking at your circuit, they know that anywhere on that red wire, the voltage is going to be 9, okay, anywhere on there. So it's 9 volts anywhere where the thing is red. And they know that it's going to be 0 volts anywhere where the wire is black. Okay. So now if you look at this wire, you look at this resistor here, you see he's got a red wire on above him and a blue wire below him. So the delta V, or the voltage drop across just this one resistor, is the same as the battery voltage. And the delta V across this resistor is the same as the battery voltage. And the other one is the same, okay? Oh, so Griffey is at, I'm sorry. Well, it's okay, I'm gonna say your name, Griffey. It's not an embarrassing question, it's a good question. I bet you there's other people that have the same question. Griffey is asking, how do you change the color of the wire in Tinkercad? Okay, so let me go into here, oops. Okay, and let me get rid of all these drawings here. Okay, so if I go into Tinkercad, I create a new circuit. Oh boy, Zoom has its problems. Okay, so I'm going to create a new circuit and hope it takes, okay, there we go. Tinkercad sometimes is agonizingly slow. Okay, so here we are. So let's bring in a breadboard. Where'd my breadboard go? There it is. Okay. So I bring in a breadboard. Come on, what does it matter? Okay, and we'll bring in a battery. Okay, and now I'm going to connect a wire. So notice that's the negative side of the battery. Okay, so I'm going to connect it up here to there. And so now, oops, there. Okay, so now the question is, how do I change the color? Well, as soon as I've connected up my battery, it gives me this, and it gives me these options here. And so if I use the pull down here, I can make it be whatever I want. So since this one is connected to the negative side of the battery, in fact, let me zoom in there. So you notice how it's already black right there, and when I hover over it, okay, it tells me. So here I hover over the red one, it tells me it's the positive. Okay, so then what I do is I connect a wire from there over to here. Okay, but the default is green, and since it's connected to the battery, I want it to always be red, so I make it be red. Okay, so that is the rule that I'm going to follow with you guys. Okay, make sure you get your red and your black batteries wires right. Now, while we're at it here, let's say that we've got some circuit that's got a couple of resistors in here. So let's say I've got a resistor right here, connected like that. And then I've got another resistor maybe like this, connected like that. And then let's take this red one here and let's connect it down here like that. Okay, so what is the voltage inside this? In fact, tell you what, let's do it this way. Let's connect it like that. So now when I have a wire, it goes from here to here. Okay, so I know that the voltage on this red wire and anywhere on this column is always going to be 9 volts, no matter whether I've got the switch turned on or not. I know the voltage here is always going to be 0 no matter what. This green wire here is going to be something in between. It's not going to be 9, it's not going to be 0, it's going to be something in between. So then it can be any color we want. I don't really care whether you use green, orange, turquoise, blue, I don't care. Just don't use red or black. Red or black, those are reserved for these guys right here. Okay, hopefully that makes sense. Okay, So let me ask you to please read the rest of the chapter. You're gonna, as you scroll down here, you're gonna see something that hopefully looks familiar to you. Remember this table here? This table is a very good tool. I want you guys to get in the habit of using these tables. Notice how the E value, which is what I like to call V, but your book likes to call it E. Notice how these numbers here, they are always the same number. That was not the case back when we were doing series circuits. When we were doing series circuits, the voltage across this resistor was different. But now, because we're in parallel circuits, the voltage across each resistor is the same. The voltage across R1 is 9, voltage across R2 is 9, voltage across R3 is 9, and the total voltage is 9. Okay, so I'm not going to read the book to you. I think you guys can do a good job of that on your own. But I definitely do want you to read this. And then when you get down to this part, okay, so here they're talking about how to do it, how to calculate total resistance. We have already gone through and done that, but the book does it in a slightly different way. And so I'd like you guys to get used to doing it. Also, the book writes the answer in a slightly different way. Notice what I wrote looks to be very different, okay? But it's really not. I mean, I said that 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. And the book said this, but you see, it's this and this, they really are the same. All we did was we just flipped, we just flipped it. We put 1 divided by this, and we got the same thing. So so you're good with this. Okay, once you get down to this part right here where they start talking about their computer program called SPICE, so at that point you can stop. So stop at this point here. Okay. All right. Now when you go into Canvas, you will find that there's a quiz waiting for you there. Okay, so after you click on this link, there is a quiz down below, and you can see it's down here. I don't want to give you too much, okay, but it's down there. All right, so that's your homework for the night. I think that that's good enough. Now we still got a good 25 minutes left. If you guys get working on this, then maybe you can get it done before the class is over, and then you won't have any homework. You got any questions? Okay, I see that Henry is saying that he hates sig figs. Ah, but Henry, sig figs love you, whether you love them or not. And you better get used to using them, because when you get into my physics class, we are definitely going to be using sig figs a lot. So get used to them now. All right, I'm not seeing any questions, not hearing any questions. Last chance, going once, going twice, sold. Okay, so before you leave, please type "buy" into the chat box. And then if you didn't do the midterm exam, do it. Do it before next Tuesday, because if you don't do it by next Tuesday, you're going to get a 0. Getting a 0 on a midterm exam makes it really hard to pass the class. Okay. All right, going to stop the recording and end the class then.